Hello, welcome to Neoscribe. There's an energy source so powerful that it could potentially provide more energy in just 1 hour than the entire human civilization uses in a year. That energy source has a virtually unlimited supply lasting for billions of years. We're talking about the sun, and it's going to be a major part of how we power modern life in the future. So welcome to the first video of a new series that aims to explore the future of energy, beginning with solar power. Harnessing the power of the sun starts with the photoelectric effect principle, which was first observed by Heinrich Hertz in 1887. The photoelectric effect is the phenomenon that occurs when light strikes certain materials, releasing a current of electrons. And that is fundamentally how solar or photovoltaic cells work. But the challenge that scientists have faced over the years has been improving the efficiency of energy harnessed from a given amount of sunlight. You see, when light strikes PV cells, most of the energy is lost by reflection or as heat. Take the first solar cell, created by Charles Fritts in 1883. It was made out of selenium with a thin coating of gold and only converted between 1 and 2% of the sun's energy. It wasn't until the 1950s that scientists at Bell Labs discovered that silicon was more effective than selenium. And this allowed for PV cells with 6% efficiency. But the cost of production at the time made them only practical for special uses such as on spacecraft. At this point, scientists were ready to face the second challenge of lowering the cost of production. And this surprisingly brings us to the Exxon Corporation, which funded research in the 1970s that led to PV cells being made from cheaper materials. And this dropped the price of PV cells from $480 per watt all the way down to almost $100 per watt, adjusted for inflation. Today, most modern silicon solar panels are either monocrystalline or polycrystalline. Monocrystalline PV cells are recognized by its dark color and trimmed corners. Each cell is a thin slice of a long cylinder of silicon. And then polycrystalline has a bluish color and are made out of molten silicon poured into very thin films. The top commercial PV cells today have efficiencies of around 20%. On top of that, the cost per watt is expected to drop to just 22 cents by 2022. With today's high efficiencies and low production costs, solar power is now the fastest growing energy source, making up 2/3 of net new capacity globally. Global photovoltaic power capacity broke 1 gigawatt for the first time in the year 2000. Today, global PV power capacity is well over 500 gigawatts, accounting for around 1% of the world's electricity generation. And according to a recent report out of Norway, global solar electricity generation will grow 65 times by 2050. There's so much room for the technology to grow, as well as there's so much room for the technology to improve. Back in November, the Institute for Solar Energy Research in Hamelin, Germany, developed a solar cell with an efficiency of 26.1%. This was achieved using surface passivation. The technique involves 2 thin layers of oxidized and crystallized silicon called passivating contacts that are sandwiched between the solar cell and its metal contact. The contacts add efficiency by healing broken atomic bonds on the silicon surface, along with preventing electric charges from being trapped in the system. The institute in Hamelin is working with other research institutes and equipment manufacturers across Europe to streamline their design for mass fabrication. So surface passivation may help commercial PV cells efficiencies come close to 27% in the near future. You see, a majority of commercial solar cells are single junction, made from a single material. The problem with single junction cells is that they can only capture energy from a particular segment of the spectrum of light. Because of this, the maximum theoretical efficiency for a single junction solar cell is around 35%. However, the highest PV cell efficiency ever achieved was 46% and was collaboratively developed by a handful of teams out of France and Germany in 2014. And they achieved this by creating a multi-junction solar cell using multiple materials. And by doing this, the multinational team was able to capture a greater portion of sunlight. And for multi-junction cells, the maximum theoretical efficiency is 87%. For now, multi-junction cells are only practical for very specialized uses like Mars rovers. They're too costly for mass production, but hopefully breakthroughs in the future will change that. Another emerging technology in solar energy is organic photovoltaic cells, or OPVs. OPVs are made from hydrocarbon materials, namely plastics. Organic photovoltaic cells are more environmentally friendly to make compared to silicon-based cells. You see, silicon is made from quartz, which is heated in a furnace, emitting sulfur dioxide and carbon dioxide into the atmosphere. Additionally, OPVs, being plastic, are flexible and can be used on curved structures, along with various items such as backpacks. OPV technology is starting to leave the lab and make its way to actual projects. In 2017, the French company Engie installed the largest OPV system, measuring 530 square meters, on top of a school. The experimental system has an efficiency of around 13% and produces around 24 megawatt hours per year, which accounts for around 15 to 20% of the school's power needs. But it appears that efficiencies in OPV cells are starting to catch up to commercial silicon PV cells. Researchers from the University of China developed an OPV cell with an efficiency of 17.3% by incorporating an incredible tandem cell system. Similar to a multi-junction PV cell, the university's cell captures multiple wavelengths of light by using devices built within the same cell structure. This was an incredible advancement from China. The only question is, which country did they spy on? Just kidding. But seriously, which country? Anyway, the challenge for OPVs is improving its lifespan compared to silicon cells, which have lifespans of around 25 years. Researchers will have to find ways to improve OPV's durability against exposure to the full range of environmental conditions. Now let's talk about another emerging technology called concentrator photovoltaics, or CPVs, which uses lenses or mirrors to focus large areas of sunlight onto a small area of multi-junction solar cells. The brilliance behind this technology is that the mirrors and lenses are low cost and maximizes the production of the costly multi-junction solar cells. But the challenge scientists face with CPVs is allowing the technology to be optimal in a variety of conditions. If the sky is cloudy or even if the air is polluted enough, the sunlight cannot be concentrated. Now let's go on to another concentration-themed solar technology called concentrated solar power, or CSP. Just like concentrator photovoltaics, concentrated solar power focuses on solar energy from a large surface area to a small area. But instead of harnessing light, concentrated solar power harnesses the heat from the sun. The heat is applied to liquid salts, which is used to boil water and run a steam power generator to produce electricity. This is the same fundamental concept as a coal power plant or a nuclear power plant, except for the fuel comes from the ever-present sun. There are two branches of CSP technology. First are solar troughs, involving long curved surfaces that focuses sunlight onto tubes containing liquid salt or some kind of oil. The liquid heats up to 350 degrees Celsius, which is then used to heat water using a heat exchanger. The second branch of the technology is solar towers, involving a large group of mirrors called heliostats that focuses the sun's energy on a single point on top of the tower. This heats liquid salts to over 1000 degrees Celsius. They look really cool and futuristic, but the downside to the towers is that they're more complex and expensive to construct compared to solar troughs. Another downside is birds. You see, the Ivanpah solar plant in California has killed 6,000 birds per year, zapped by the plant's 3 solar towers. But I must point out that the plant has since installed a respiratory irritant to keep birds away from the towers, so hopefully that makes a difference. Alright, CSP research has a bit of ways to go in order to compete with photovoltaic systems. However, the technology's ability to store energy could make it a viable competitor down the road. You see, the liquid salts stay hot throughout the night, continuing to generate power, which is something that photovoltaics cannot do. And concentrated solar power is just a small part of the frontier of solar tech research, pushing the boundaries of solar power technology, making it increasingly cheaper and more efficient. From multi-junction solar cells to concentrated solar power, the landscape of solar research extends beyond the horizon. The sun has a virtually unlimited supply of energy, and it's going to power the future. Alright, that's all I have for now. I hope you enjoyed your journey. If you did, please leave a like and subscribe. I am Neil Scribe, and I'll see you on the next journey.